the characters, and which I guess the equation that you have, that value, which is the trace of the matrix that we're
Yeah, I
using.
mean, it's idiotically simple. You wouldn't think it's very important. You
Right,
know,
right.
I mean, trace of matrix, it's obviously invariant under similarity transformations because it is, but so what? You know? So I find it totally amazing that that's all. You don't need
Which I
anything
guess
else but a trace.
which I guess is what I guess we're looking for clarification for as well, because I think I mean, what are you using? So the three phi values that you use, A1 and A2 and the character one, could you, I guess, touch on what you're using those values for? Because everything on the right hand side, where you have I guess the different classes grouped together and then I guess averaged out, I can understand, I guess, what the components are, but could you touch on what the use of those
The
values are?
characters.
Exactly, right.
So, the first thing about characters is I showed you that Fourier transform is a multiplication of a position vector by unitary matrix such that the result is diagonalized. So diagonalization transformation is just this multiplication by unitary matrix. And this unitary matrix is very simple. It's roots of unity to various powers because it's just e to the 2 pi over L, which is, how many things you have, multiplied by the two indices, K and J, So it couldn't be, if you're just playing, right, trying to say something is a matrix and I build it from a single number, you would do that. You would take a number and you would raise it to the powers. But because it's a complex number, it remains, as you raise it to the powers, it remains complex number of unit length. So that's what happens in Fourier analysis. You say, whenever I have to have a law which is invariant under where I measure, so only thing that is important is separation of the points, but not absolutely where they sit. Then I have to use Fourier modes, and if I do that, all the matrices just become diagonal, they become numbers. Or, every reducer representation, I apply 10,000 dimensional matrix doing God knows what, and it says answer is 7, just gives me one number back. So that's an amazing deduction. Now when we go to the next thing to have non-abelian groups where you add a symmetry which starts mixing these guys up in a non-abelian way, meaning order matters, how you do it. Then you say, okay, the whole thing has fallen apart, there is nothing to do, some nonsense happened. Now what happens is that it still retains this unitary weight. It used to be just root of unity to ijk, but now it belongs to the whole subspace. The whole subspace has one weight. And this weight turns out to be, again, root of unity. And it's called character, and it's this trace. So, so that you don't expect when you start, you realize when you're done that that's how it has to be. But I find it totally amazing. It's such a simple answer. It just says, I used to have 7-dimensional space, and there were 7 different roots of unity that described it. They were the reducer representation. Now I say, let me mix, 3 and 5 and 2 and 6 by having a flip, by having a symmetry. Then I have fewer spaces because these guys are not distinct anymore. They're mixed up. So I should get some kind of blocks. Okay, fine. But then you think there's going to be some horrible calculation because, I have a little matrix and I have to compute all elements of this matrix, etc. And then group theory says, no, everybody in this, it's total democracy. Everybody in this subspace is equal. So they characterize only by one number. And it's again, root of unity, but it's now called a character. And it's so simple. It's a trace of a matrix. Could have been some horrible thing where some polynomial, you solved it, seventh root of something, and you get a number, right? But no, it's this really simple number, and that I find surprising. I maybe there are mathematicians or my colleagues in physics who can give an intuitive explanation, but I can only do it by doing a calculation and showing you at the end, it's really simple, but I cannot guess it's going to be simple. This answer is much simpler than, I would have ever hoped. It's, my wildest hope would, and then, because groups are abstract, you have to compute these numbers only once in your lifetime. You put them in a book. So my colleagues who do condensed matter physics never do this. They don't know how to compute character tables. There's a book of spectrographic tables, Now it's online, but used to be a book of, 6,000 pages, just full of tables, characters, and they're for all materials, there are 270 different crystalline materials in 3 dimensions, and, there's a character table for each one, and you take it, you stick it in computer, and you get the irreducible representation, and you expect the spectrum, and then you do experiment, you say, this crystal is on angstroms, I cannot see it, but it's producing all the right spectral lines, meaning irreducible representation, that says it's this particular crystal. It's a face center, cubic something, da, 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 da. So you can see the atomic structure by doing measurements. That's what matrices are, they're operations. I do something to the system, and the irreducible representation give me numbers back. And these numbers are, the ones that character table tells me I can see. That's it. I'm done. So, that's how we know about silicon, germanium, semiconductors, high temperature, low temperature, graphene, all these things where we are building electronic devices and microscopes. As long as we're in a linear regime, and quantum mechanics happens to be linear as far as we can tell, that's how it works. So that's the basic tool. Now, it becomes a life profession to produce one book of this table or do a research with new materials. But that's the tool that you use. I mean, you're indoctrinated, you just need your character table. So if you look at chemistry books, they're full of these tables. That's what they are. They're diagonalizing unitary matrices. I do this to my system in 3 dimensions. I see that. These are these lines, spectroscopic lines. They're the eigenvalues. They're the things that identify irreducible representations. Then, they have more information than we do here, but you learn it in quantum mechanical courses. They have magnitude, they might have a width if they are metastable and stuff like that. There's lots of other technology, but this is the backbone of everything. So all linear problems, you solve them this way. There's a matrix, it has its natural coordinates. And in natural coordinates, things get simpler, and natural coordinates turn out to be irreducible subspaces. So that's it. Everything you can do with linear problems. It's pretty amazing. But amazes me about linear algebra, you would think this was all done, who the hell, in 1840. I mean, why would we, why is there a Journal of Linear Algebra today? Well, you're trying to identify faces and faces in motion in videos. And how do you do it? You write some kind of array of 3 numbers, which is a tensor, and you apply a linear operation that maps this face into an eigenstate that's called, Chinese or whatever. Yeah. And you discover, yes, that's what you're doing. And if you're stupid, it takes you a month. If if you use good algorithm, which is a generalization of fast Fourier transforms, but in more dimensions, tensorial algorithms, it takes 10 to the minus 6 seconds, and yeah, it goes on. It hasn't stopped. So what I find interesting is fast Fourier transforms were discovered like 50 years ago, or maybe even less. And everything. I mean, your phone could not work without the image that you're seeing. Everything is being computed by fast Fourier transform, coded, transferred, etc. And it's only, it's very recent. Somebody said, let's think carefully. If I use powers of 2, because that's the simplest prime number. You could also do it in powers of 7. There will be also a fast Fourier transform. But let's do it in powers of 2. Blah, blah, blah. And then instead of multiplying, n squared times, it's n log n, and that's a big deal.
Right.
And that was done in linear algebra, and the same thing they do in neuroscience now. There are all kinds of results of how do you control muscles, etc., done by linear methods. You would think brain hopefully is not linear. Well, global it's not, but there are lots of pieces where it's very useful.